Okay, I hit start. Hello, YouTube. Today we're having, what's likely going to be an abbreviated section on the first part of Chapter 11 in the Introduction to Statistical Learning with Python book, which is about like survival models, sometimes called like censored models, censored regression, a lot of different nomenclature for the same thing. And yeah, just to kick off, so well, I'll jump to this slide first. So the kind of big conceptual starting point for this chapter is that there are a lot of times where we want to study a phenomenon where what we're observing aren't the sort of true values that we want to study, but sort of what we call censored values. So the sort of simplest, most intuitive case is in the case of like a study of the time till death, which is why these models are often called survival models. And I think they actually did have their kind of origins in like population longevity studies. But yeah, so we can see like, say we're studying a cohort of individuals and we're measuring their time till death. Maybe they have a disease or something, and we study them for 10 years. After the end of 10 years, we take a snapshot and we see who survived and who didn't. But actually what we're really interested in is, and I'll jump to the next slide. At least in this kind of toy example is like their true time till death, which is the extended blue lines here. So you can see we stopped the study at time t, but we, if we, kind of had all the information that we wanted, we would have been able to observe the participants until, the end of this chart, I guess, at time t equals 25. So we're kind of missing information that we would like to have, and the missingness is caused by this kind of artificial censoring process. And so yeah, I don't know. I wanted to highlight the Python packages just because this is a Python book. So the kind of key Python packages for this survival analysis, these are supposed to be hyperlinks, so I must have messed up my Quarto, but I'll go back and fix that. But the kind of the one that the book uses in its exercises is this lifelines package, which kind of presents the API is kind of conceptually modeled on this kind of classical statistical approach to survival analysis, which is the approach the book takes. So I think it, especially having read this chapter, it will feel like kind of the most intuitive and kind of most approachable. And the documentation is actually pretty good. I think it's worth probably looking through if you are curious about this. Which isn't to say the documentation for all these packages is good, but the Lifelines one is kind of the most approachable, I'd say. The other kind of big package is Scikit Survival, which integrates with the scikit-learn API that we've been using a little bit throughout the exercises in the book. A lot of the sort of the book package, I think, functions to like conform some of our the other statistical packages to kind of the scikit-learn style. And so this is nice because it implements kind of like the maybe like more modern extensions of survival models using random forest, or I think there's a couple other there's like deep learning approaches and all kinds of stuff. Which brings us to this PyCox package, which is sort of integrates with TensorFlow. Oh, excuse me, not TensorFlow, with PyTorch, and that lets you run these on GPUs. So that's all fun stuff. But so for this, just the Lifelines package is really the only one that we use. Maybe, I don't know, we'll see. Maybe next week we can try to use the Scikit survival one for a random survival forest, apparently is what it's called. Sounds very frightening. Okay, so, and I should have cropped this maybe, but so this is, oh, sorry.
Question there on the, obviously it's survival analysis and it gives one example of non-medical usage. But I'm trying to think if there's like a conceptualization of where these models are useful. Not where these,
Yeah.
but like, because it gives the example of churn, where it says customers cancel subscription to a service, and you're basically tracking it up to some time point.
Yeah, and I actually found this like maybe, and I've made another Quarto mistake I see down there, but sorry. Yeah, like maybe almost more conceptually difficult chapter than like a like mathematically difficult one. But yeah, like it's one of those things where you kind of know it where you see it just because of the like core example of like time till death. But yeah, like I think conceptually it feels like okay, like censoring, it's a case of like missing information. Um, but that's actually quite a broad category, like and maybe in some ways it feels a little bit like causal inference where like you have an observed quantity, but you really want like another unobserved kind of quantity. So yeah, it does feel a little fuzzy, and like it might be that there are other models that can do this type of analysis as well. I don't know. That was kind of my thought, but I certainly, yeah, like the kind of all the like off the shelf models are structured for this case where you have a time sequence, and then there's some kind of like event in each period of the sequence.
I guess that's the key, isn't it? This time
Yeah.
for an event. Because I'm trying to think of like, I don't know, I've been thinking about like risk models at the minute and
Hmm.
time until event. I wonder if like insurance, when you're trying to model, if you're an insurer, you want to know the first time that like a person is going to crash their car, and you have
Hmm.
some information on the first time that people crash their cars, and then you've got like this group who haven't crashed their cars yet, and it's like
Hmm.
when it's going to happen,
Yeah. Yeah.
given all this.
Yeah, I think that would be appropriate. So that is, and so there's different kinds of censoring apparently, and so we don't really talk about any but the kind of like the paradigm kind, which is right censoring. So like, and that comes from like the normal layout of a timeline. Like a timeline goes from, I think I might be mirrored, but like from I don't know how, but from right to left, timeline go or from left to right, timeline goes from left to right. I'm not sure if I'm mirrored or not, but so like a right censoring is kind of like where the censoring occurs at the later in time, and left
Mm.
censoring is when it occurs earlier. If you're looking at first car crash, I guess that would be right censoring because you're
Yeah,
kind of
I
waiting.
think
Yeah, yeah,
right censoring is always like, I can't look into the future, which
yeah,
is quite
yeah.
intuitive. Whereas you're like, why can't I look into the past?
Yeah, yeah. And I was struggling to think of an example. They said that left censoring is possible. I wasn't sure. That would be like,
I thought their example on that was very confusing.
I don't remember what it was to be honest.
Uh, it was something to
Oh, it
do with
was like
pregnancy.
something with what with like pregnancy and sickness or something like that. I can't remember.
Yeah, I
Um,
can't section, but yeah, it's like it was looking backwards where you look at 250 days after conception of a baby.
oh, right. Okay.
It's like some of the people have already had their babies by that point. But then I was confused, like, why wouldn't you just ask them how many days ago they had their baby, and then it wouldn't be left censored
Right.
anymore?
Yeah. I mean, I guess maybe, yeah, I mean, I guess maybe you're assuming they forgot or so, or they don't know, or maybe
That's
they
the
drop out. Maybe they drop out because they're busy parenting. I don't know. But
yeah, that's the
yeah, it
bottom
does.
of page
I don't,
471 example, just
yeah.
for
And it does seem like a lot of censoring results not like because of like an in principle limitation, but more because of like a practical one.
mm,
Um, and I mean, so this is, and this is from like a Google search, but like some of this stuff is like censoring can occur because like the participant just like stops, like falls out of touch, or like maybe there's some protocol violation. So that's not really like those are like in principle avoidable maybe, but like they do happen in real data. So you're kind of trying to account for that. But yeah, I did find that confusing. And there's also this third category of interval censoring, where you would have like you don't know when something happened, but you know it happens in a period of time. I'm not sure. Oh, and these should be T's. I've many mistakes. Why it should be T1 and T2. Um, but yeah, I struggle to think of an example for that. Like, yeah,
I wonder if like if there's some sort of events that are happening before records began in that sort of sense.
yeah,
And
I guess that
again,
could be,
not um
yeah, um,
like I'm trying to think of an
or
example.
I don't know. You could imagine some sort of like, uh, maybe there's like a failure of your hard disk or something, and you lose all the data from like January to February, and then you can that you had an event. For anyone who's dead after February, that you had an event somewhere in that period, but you don't know when. I don't know, something like that.
Yeah.
But yeah, so some of these, and yeah, I mean, I think this is pretty straightforward. This is just their kind of notation, but the idea is that we kind of wish that we were observing this quantity t, but actually we see y, which is either t or the kind of censored outcome. Um, and yeah, so I don't know. I pulled up some of these kind of questions from the end of the chapter about, so they don't really get into ways to control for, well, let me back up. So like an important assumption of these models when you use this strategy is that your censoring mechanism is independent. I thought I had that on the slide. I guess not. Oh, no, I do. Yeah, the censoring is conditionally independent of the uh, sort of time of event. So they don't get into ways that you could kind of control for that. You could, use like different combinations of covariates and stuff, but they did kind of ask these questions at the end about whether or not these different scenarios met that assumption. And I thought some of like the last one in particular, I thought was I don't know, I wasn't sure about, but so the first, I don't know, I mean, I could just like wing through the first three, but like in this first one, in a study of disease relapse due to a careless research scientist, all patients whose phone numbers begin with the number 2 are lost to follow-up. I think this depends a little bit on how phone numbers are assigned, but like I think oftentimes the first number is meaningful. It's either like a country code or like maybe a zip code, so it'll have some geographic connotation. So in that case, like your censoring, I think, is probably not independent of your uh, sort of chance of relapse if it's they're kind of co-determined by your geography. Um, in a study of pregnancy duration, women who deliver babies preterm are more likely to do so away from their usual hospital and thus are more likely to be censored relative to women who deliver full-term babies. Yeah, so that I think is definitely a violation of the kind of conditional independence, or the independence at least. Maybe you could control for that, but the fact that you're more likely to be censored if you're uh, uh, more likely to deliver preterm is like just kind of like a definitionally violation. Um, Researchers conduct studies of disease-free survival. Patients who have not relapsed within 5 years are considered to be cured, and thus their survival time is censored at 5 years. And I don't know. I was a little confused about this because in some ways this seems like the classic case, like all
Hmm.
studies and um and so is this a case of independence? I think I want to say yes, because everyone gets this it's applied across the board, the 5 year censorship, regardless of uh your uh disease free state. But yeah, I'm not sure if you have any thoughts about that. I think that's supposed to be a clear case of independence.
Yeah, that
Um,
seems like a pretty classic case. I don't
yeah.
know. I guess the event here is relapse.
Hmm.
So the event hasn't occurred within 5 years. So it's censored at 5 years.
Yeah. So your chances of
Yeah.
relapsing are not related to your to your chances of being censored or your time of censorship, I think. So yeah, that's an independent.
I guess
Um,
that's But it could depend on the length of the study. It doesn't say anything about the length of the study. If the study was
Right.
3
Yeah,
years,
that's true. Like if the study was 10 years, but you counted them as cured after 5, then
mm,
maybe that's problematic. Like
if the
you're
study was 3 years,
right. Yeah. Yeah. That's a good
they
point. Yeah.
only have them as three. Oh, but then you wouldn't know. Yeah,
It would be strange to count them. Like no one would ever set the cure time different from the length of the study. I think like that would be quite strange. Like if you had a short study and you set the cure time longer, or if you had a long study and you set the cure time shorter, that would be like quite, I don't know. I don't know why anyone would ever do that. But that I guess could be problematic. You're certainly ignoring information in either case.
yeah. In the
Um,
3 year example, then your censor time would be 3 years, so it
yeah,
wouldn't matter that you're censoring at five
yeah.
years. And in the
Um,
for the longer study example, maybe if you've got new people coming into the cohort, and so their timelines don't start at 0,
mhm.
then you might have like a
Yeah,
roll. That's more like a rolling study, though, right? I don't know if
yeah,
that works the same.
yeah. I think that certainly is a case of censorship. Although I think you have to use like I think the model gets more complicated. But yeah, like basically, and maybe this is a little bit what this last example is getting at, where you have yeah, like staggered treatments or staggered start times, um,
Mm.
where like basically people have different like in the same time period, people will have different the censoring is actually occurring at different places in the treatment for individual participants. Um, so, is that a violation of conditional independence? Your chances of uh, being censored are related to your survival time. Um, yeah, I don't know. I'm not sure about that. Like it certainly, and I don't know if you know the answer to this one, but I think this is that what you just described, the case where you have staggered start times. And I'm not sure if that's a violation of independence, but it certainly is something that you need to take account into the model. Um,
In general, we need to assume that the censoring mechanism is independent, conditional on the features the event time t is independent of the censoring time. So my reading of that is if the location is in your model, if it's a feature
mhm,
in, then the event time t isn't independent of the features.
mhm.
But if the location isn't in your model, then how do you deal with having two censor times? I don't know if that's just in a part of the
Yeah,
chapter.
no, I agree. I think you have to have, um, yeah, like in this case, like maybe like a dummy variable for Iowa or Pittsburgh, um, or like something more complex if you have lots of different, factories. But yeah, you have to take into account somehow the fact that uh, they have, they opened it at different times. Yeah. Uh, okay. So now I'm jumping into this concept of the survival curve. And again, like maybe or mathematically easy, but I was a little confused about it conceptually. But it's like pretty simple to wrap your mind around. It's just the probability of surviving until time t, lowercase t. So the probability that your survival time, uppercase t, is greater than the cutoff point, lowercase t. Um, and so if we wanted to make an estimator for this, and I should have put a little bullet saying this, but we could just try to take the proportion of people who lived until time lowercase t, but that I guess is excluding information about people who were censored before time t. So like if you quit the study or like maybe died from another cause, if you're trying to study like a particular cause. Um, and we also just can't take the proportion of like just change the denominator to the non-censored individuals and just take the proportion of surviving non-censored individuals, because that includes information about how long all of the censored individuals kind of made it before getting censored. And so I think that makes sense. One question I had about is in this conceptualization where your kind of quantity of interest is the probability of surviving till time t, do we need to worry about right censorship at the cutoff time? And my feeling was no. I think at least the way it's conceptualized here is that like if you only care about survival until time t, and not like total survival time or something like that, or like then maybe in this kind of survival curve model, you're actually not treating T as a censoring point. It's just kind of like the end of the study, but you're not looking to, you don't care how much longer people survive than that. That's just like
Mm.
totally irrelevant to your question.
The
Um,
lowercase t isn't the cutoff time.
so it is the cutoff time. I think in this conceptualization, I don't think they're treating the cutoff time. So like in this one, they're treating the cutoff time as a censoring point for sure. And I was a little confused by this, but like I actually think in this one, they're not treating the cutoff time as a censoring point.
Well, it
Um,
can't be the cutoff time because you're left. It's a function of that lowercase t. So this is just your time variable. Then your cutoff time is some time within that. I think.
um,
So that's why, because otherwise your plot would be constant because lowercase t would be constant at the cutoff time.
uh,
I think.
I think, yeah, that's right. Yeah, so T is each period. You're right. Like in every period, there's a different T. Um, but I also think that uh, like we're not looking past um, like when we're calculating the odds of survival in period one or whatever, we don't
Mm.
care at all about any future deaths
Ah,
or survival, I guess is what I'm trying to say. And at the end of in the kind of the final, yeah, sorry, I should have, you're uh you're right. Like T is each period, but then at the kind of the final T, the final period, um, we're actually not saying like, oh, I wonder if anyone lived past that. We're just saying, okay, this is the end of the study. Like, who cares how much longer people live? Um, I think is kind of how they're treating it. So like the the future, each the later estimates incorporate information from the earlier estimates, but the earlier estimates don't incorporate information from the later ones. That's, I guess, what I was trying to say. I don't know.
mm.
Um,
What's
uh,
in the brain cancer data set? Do you know what the cutoff time is? Is it 20 months?
and sorry, and what? I'm actually, yeah, I'm not sure. Um, uh, yeah, I think it's 20 something.
Oh no, 'cause
Yeah, 20 months. Yeah, 20 months.
it doesn't. I can't see anywhere where it says the actual length of the study. Oh, so it just uses 20 as like an example point, does it?
Yeah. Yeah, I think 20 is just the example. But uh, yeah, maybe I think there's some messiness in kind of how T is defined. Like I think, well, no, I think that's right. Like I think T is just the latest, like chronologically latest time period. So like if your study ends at 20, then it's just 20. And then you specify the lesser periods with this, like the in-between periods with this decay, I think. Um,
That's the
uh,
times.
which is
Um,
like the time of death, each unique time of death. Wait, should I? Yeah, so like the way this works, and I'll try to explain it, is that you can imagine that you have, say 10 people, and they each have they either die or don't die, but for the ones who do die, they have a unique event time, which might be, which is in this case, their death. Um, uh, Before each unique event time, you might have dropouts not due to death. So like, they lose contact or whatever. Um, and so you're basically calculating of the people who could have died in each time period, how many how many survived. And you're calculating that for each time period, where the time periods are defined by like the devs or the events. And then you're multiplying those together as like independent probabilities. I think. And so yeah, I have colloquially this fraction is the percentage of at-risk individuals, so like the people who like could die, who survived past the each point at which someone did die. So like if you're in the first period, maybe you have 10 people who are potentially able to die, and then at the end of the first period, someone does die. This would equal, if there's no other dropouts, then this would be 0.9. If there are other dropouts, say one other person drops off, but doesn't die, but just drops off, I think this would be it'd be like your denominator would change. I think your denominator would go down to
Yeah, because your risk size
reduces.
reduces.
Yeah, your risk size reduces. Yep. And so the key, I guess, for this estimator is basically this kind of multiplication step where you're taking into account information from every time period instead of just a snapshot at one time period.
It's like the probability of not being the first person to die and not being the second.
Yeah.
And not being the fourth.
And I did have this question. Well, here's this first question, which I guess we just talked about. It was like, what information does this capture that we were kind of ignoring before? And yeah, I think it is that like sequential nature of it, or like the fact that each time period before has some information that we're incorporating. And then I had this question, which is like, if no one ever dropped out of a study, would we need this estimator? And my sense was no. And I don't know, I'm glad you're here, because I was kind of trying to like figure it out. But I was like, if there are no dropouts, then you're just in each period, you just lose one. And so then the sum of, or not the sum, the product of these consecutively just subtracting one each time, I think is just the at-risk population minus the number who actually died over the at-risk population, which I think is just the proportion of surviving people at the last point in. But I'm not sure about that. I did ask Claude, my good friend Claude, and he seemed to agree. But they're agreeable. He's an agreeable guy, so not sure about that. But yeah, I do think if you have no dropouts, then you don't need this. Then you just can use the simple naive estimator, the proportion of survivors at the end of the study.
In the equation 11.3, where is QJ defined in this?
What do I have QJ? QJ is the number of patients who have died at time DK.
Okay, so that needs to increment every time.
Yeah, so every time, and I don't know if I have written this correctly, but this is just supposed to be, +1 for each time period. So I think K. I don't know.
I don't understand how that case come at the end if you take product of them all.
Because uh, for each time period, you're just subtracting, like you're just losing one.
Then you're
And
taking the
so
product.
at the very end, you're basically just subtracting off from the total, uh, uh, you know,
But it's
1
probably
times K. Um, but I don't know. So I didn't really figure this out. This is like more intuitive to me than uh, like, a proof. But because if there are no dropouts, uh, then I don't think you need to incorporate kind of this past information, basically. Like basically there is no extra past information that is relevant to your question. Like if you're wondering like, okay, like how many people lived till 20 months, if no one dropped out, then you just know like, oh, these people lived till 20 months. But if there were dropouts, then suddenly you're in the world of counterfactuals where like, oh, this person dropped out, but like they could have maybe survived. So like, how do we, but like if you aren't worried about that, then you don't need this, I think.
with this
Um,
estimated probability that you survive until T, it's the probability that you survive longer than DK,
mm,
not that you survive less than.
until, yeah,
I think
that's a good, yeah. Well, actually, did I do that right? Is it greater than or is it greater than or equal to? I should
it's
look.
greater than, yeah.
Yeah, that's a good point. Okay, so maybe there is um something that I'm missing there. But I don't know. That was just kind of a question that I had. Is like I think in either case you should use this because you know I think you're not worse off by using it, except for maybe like the labor of implementing it. But like um but I don't know. That's just an open question. I maybe I'll look this up and see if there's an answer. Um, and so yeah, here's one of these survival curves with some uncertainty shading. And yeah, I mean, I think these are pretty intuitive. Like as time goes on, your chance of having survived until, or I guess not until, but uh, till just after that point is goes down, which makes sense. And I guess my chart, I thought I copied the chart where they broke out the survival rates for men and women, but I guess I didn't. I'll put that back in. But in the cases where you have, subgroups, and you're wondering whether there are sort of meaningful differences in the rate of survival between the different subgroups, you kind of run into similar problems with censorship. You might be, so in this case, they're looking at differences between the survival rates of men and women. You might be tempted to just use a sort of a paired t-test, a two-sample t-test to say like, okay, like this many men survived until 20 months and this many women survived until 20 months. Is there a difference? But you can't do that because, again, censorship can occur sort of dissimilarly across groups. You could have like more censorship in one group or the other. And you could also have like a different sequence of censorship, both, I think, which would be relevant. So the kind of solution to this is a sort of a modified version of the sort of classic like Z kind of statistic. And in the book, they kind of go through, they like derive it from the Z statistic. But this log rank test, I think it's named after a person too. By
Cochrane Mantle Hansel test.
yes, right. So not to leave those fine people out. Yeah, but so basically, but the sort of like core logic is the same, where basically you're trying to compare the sequence of dropouts across groups rather than just this kind of point at the end. And I didn't dig into this as much as I wanted to, but you can see that essentially you're breaking out the parameters from the earlier equation by group. Man, I made a lot of typos in this little slideshow. But you're taking the, and I'm kind of winging this, for group one, you're subtracting the mean survival number in each period, and then dividing by the sum of the intergroup variance. I have to look back at the book. Let's see. Sorry, that's so no. Then you're dividing just by the standard error of the Q1K, which is the survivors, a number of survivors in each period. So I don't, yeah, I don't know that I have an intuitive understanding of that equation, but and I've mistranscribed it here because I was in a bit of a rush, but you know, the core logic is the same. It's like, oh, okay, you want to incorporate information from each period. And you can see it looks like a Z statistic where you have like, you know, the group mean minus the sort of paired mean or pooled mean over the standard error. But it's just modified, I think, to kind of take into account this stuff. But yeah, I honestly I should kind of scrutinize that a little bit more.
Yeah, so it's kind of just, yeah, like you said, it's like a Z statistic, but over each group and then added together.
Yeah, yeah.
That makes some logical sense.
And I think, you know, that's kind of all I have. It's I think analogous to a p-value, this statistic. So like it lowers values way against the null hypothesis. So like I think this is the output from that test of sort of men versus women in their survival rates of brain cancer after 20 months, and the sort of test statistic. Oh, well, they're reporting different things, so maybe I need to double check this. But so I guess the test statistic is 1.44, and then it's calculated from that a p-value. So you know, this p-value, I guess, is, you know, relatively high. But I actually don't know how to interpret this test statistic by itself. But yeah, I mean, that's kind of all I got for this week.
What did it say why it's called the log rank test? I was expecting to see at least one logarithm.
That is a good question also. I don't know. Why?
Maybe it's derived like,
Yeah, maybe the,
because you've got the product earlier on. Maybe you take the log of that
yeah,
product, this sum.
yeah, that makes sense. But yeah, I don't know. Yeah,
Yeah, on that your Kaplan-Meier, I think if you take a log of that estimate, it might look a bit like, oh no, it wouldn't. It would just look like the top of that fraction, maybe. I don't know.
yeah. But I think you must be right. At some point, they're transforming that product into a sum, and maybe that's where the log comes from. Yeah. Yeah. So I guess, you know, next week is like the more maybe useful stuff. here. So I'll stop. So join us next week for a discussion of how to incorporate these strategies into your regression modeling. And I'll stop.